Welcome back to Derivatives and Risk Education. In the previous video, we defined random variables, their distributions and expectations, all based on a finite probability space. Now, in this video, we'll introduce another powerful concept, conditional expectation, how to update our estimates when new information becomes available. In this video, we'll look at conditional expectation in the context of the binomial pricing model, which we looked at in detail earlier in this series. In that model, we assign risk-neutral probabilities to each outcome of a coin toss. P is the probability of heads, and Q, which equals 1 minus P, is the probability of tails. And we use the symbols H and T to represent heads and tails respectively. Each full sequence of coin tosses, like heads, tails, heads, is called an outcome, and we denote it by the Greek letter omega. We write omega equals W1, W2 to Wn, where each Wi is either H for heads or T for tails. So W1 is the result of the first toss, W2 the second, and so on. As we saw in the previous video, if x is a random variable defined on these outcomes, its expectation is as written here. This is the weighted average of all possible values of x, using the probabilities of each full path omega. This is the unconditional expectation, which is the expectation based on no information about the coin tosses. Now suppose instead we're at time n, and we have observed the first n coin tosses. So now we do have some information. We want to estimate the stock price at time n plus 1, based on this partial information. Then the conditional expectation of the stock price at time n plus 1, given the first n tosses, can be written like this. It's an estimate, based on what we know so far of what the stock price will be next. And because the first n tosses are random, this conditional expectation is itself a random variable. Let's break this down. This is the expected value of the stock price at time n plus 1, given what we know at time n. This is the input to the conditional expectation function, the known sequence of tosses up to time n. This is the value of the stock price at time n plus 1 if the next toss is heads, multiplied by the risk-neutral probability P of heads. Then the same idea, but for tails. This is the stock price at time n plus 1 if the next toss is tails, multiplied by the risk-neutral probability of tails, which is Q. Let's generalize. Let x be a random variable depending on the first big N coin tosses. So big N is the total number of coin tosses in this experiment. Then the conditional expectation of x, given the first n tosses, is as written here, where the sum runs over all 2 to the power of big N minus little n possible continuations, and h and t count heads and tails in the continuation. This gives us a weighted average of all possible futures based on what we know at time n. Let's also break down the parts for this general case. The expected value of x, given what we know at time n. This is the probability of each continuation, and this is the value of the random variable x for a full path that starts with what we already know at time n and continues with a possible future. So we multiply each possible value of x by its probability. We don't know the future tosses yet, so we sum up over all continuations, meaning all possible sequences from time n plus 1 to big N. There are two extreme cases, when n is equal to 0, which is the expectation based on no information, so just a full average over the sample space omega, and when n equals big N, the expectation based on full information, which is just x itself. Conditional expectations can be computed under the actual probabilities or under the risk-neutral measure. We'll use both depending on the context. Now let's look at the fundamental properties of conditional expectation. And these mirror the properties of ordinary expectation, but they're indexed by time and information. So let x and y be random variables depending on the first n tosses. Then for any little n between 0 and big N, the first property is linearity. It says that the conditional expectation of a constant c1 times x plus another constant c2 times y is equal to the first constant times the expectation of x plus the second constant times the expectation of y. The second property says that we can take out what is known. If x depends only on the first n tosses, then to work out the expectation of the product of x and y, given the first n tosses only, we can take out x because it is known after n tosses, so it's effectively a constant here. The next property relates to what we call iterated conditioning. If n is less than m, then the expectation after n tosses of the expectation of x after m tosses is just the expectation of x after n tosses. There's also the property of independence. If x depends only on tosses after time n, then knowing the results of all the tosses up to time n does not give any information about x. So the expectation of x, given the first n tosses, is just the unconditional expectation of x. The final property is Jensen's inequality. We'll look at the unconditional case first. This says if x is a random variable and phi is a convex function, then the expectation of phi of x is greater than or equal to phi of the expectation of x. This inequality tells us that convex functions amplify uncertainty. For example, if x is the number of heads in 3 tosses and the function phi of x equals x squared, then the expectation of x squared is greater than the square of the expectation of x. The gap between the two sides is exactly the variance of x. Now, let's extend this idea to conditional expectation. If phi is again a convex function, then for any time n, the conditional expectation of phi of x is greater than or equal to phi of the conditional expectation of x. All that is different here, that we now have the conditioning on the first n tosses. But even when we condition on partial information, convexity still pushes the expected value upward. It's especially important in finance, where convex payoffs like options benefit from uncertainty. To recap, conditional expectation refines our estimate of a random variable based on partial information. It's computed by averaging over all possible continuations weighted by probabilities. It behaves like ordinary expectation, but respects the flow of information over time. And we looked at Jensen's inequality, both unconditional and conditional, which reveals how convexity interacts with uncertainty. In the next video, we'll introduce martingales, stochastic processes where the best estimate of tomorrow's value, given today's information, is simply today's value. Martingales are central to risk-neutral pricing. Thanks for watching. Don't forget to like, subscribe, and share with anyone learning quant finance.